welcome everyone again to this new Graviticula seminar. This time is by the hand of Bastián Díaz. He did his undergraduate, his master, and his PhD in UTFSM. He also did a research internship in Boston University and another internship in Dresden University. Sorry. He right now he's a postdoc in Munich University in Germany. So please, Bastián, go ahead, and thank you very much for giving the seminar today.
Okay, thank you. Thank you for the invitation, and in particular the organizers of this activity. I'm very happy to present here. So, yes, my name, as was said, my name is Bastián Díaz. So I'm going to talk about, this presentation is about two works, basically. And as you can read, this is the title: Assisted freeze-out of two real scalar dark matter singlets and the G-2 muon anomaly. So this presentation, as I said, it's based on two works. The first one was made with these people, Kilian Muon and Dominik Stockinger from Dresden. And the other part, the second part of this presentation, is about the work that I did with my colleague Karim Gurbani from Arak University from Iran. So if you have any question, comment, please just interrupt me at any moment. So the resume of this presentation is basically this one. The first part of this presentation is about a simple extension to the standard model particle physics, in which we are going to introduce two more real scalar, both gauge singlets, and both stabilized by two discrete symmetries, so they can become dark matter candidates. We focus on a particular scenario, which is called assisted freeze-out, with the goal to look for dark matter at the electroweak scale, evading the most stringent direct detection constraints. And the second work is an extension of the first one. So in the second work, basically we introduce a new vector like lepton, basically, which couples to one of the scalars and the muon particle of the standard model. And we look for this G-2 anomaly, and also accounting for dark matter things. So let me introduce you to the dark matter area. As you might have heard, we have a lot of different proofs, astrophysical observations that suggest that we are not alone in terms of matter. Actually, we have different observables from the astrophysical side that suggest that there exists an exotic type of matter, which we call dark matter. And these are the three examples of the evidence that we have: the rotational curves, palette clusters, and the rich information from the CMB. There are other proofs also, but I don't want to spend too much time here. But the lesson from all these observations is that is reduced basically in the right, in the picture, in the cake of the right side, where we have the energy distribution of the universe. Basically, you know that our matter that we know, the standard model of particle physics, if you want, at the fundamental level, composed not more than 5%. That is what we call the normal matter. There is this 26%, which is what we observe, as I said, from the astrophysical side, and the rest is something unknown, which we call the dark energy. So from the cosmological, from now on, I'm going to all the time I'm going to speak about this, about this parameter below here, the parameter density for the dark matter, which is basically proportional to the density of the dark matter today. And this has been measured, and it takes this value, 0.12. So as you know, the standard model of elementary particles is this one. This is our periodic table with the quarks in orange, the leptons in green, the interactions in blue, and the Higgs boson. So people that study dark matter usually add a new particle or a new family. So this is what we call the dark matter particle. And there is, the first thing that you can ask is what is the mass of this new particle? So here is a picture, not to scale, but it exemplified at some extent what might be the mass of the dark matter, and what's the name that we use to call it this depending on the mass. So probably you have heard about the WIMPs, which span this mass range from 1 GeV, the mass of the proton, to 100 GeV more or less. But of course, you have other options, as you can see here. And also in this plot, it's not only, in this picture, it's not only represented what I suggest in the beginning, that dark matter can be a particle. But for instance, in the right of this, in the yellow part, you see primordial black holes. Those objects enter in another category, machos, actually, that's the name. But yeah, you can see that there is a lot of options, and actually this is not the whole picture, but it gives you an idea of what we are looking at. So we are in this presentation, I'm going to concentrate basically on dark matter in the WIMP, in the blue region. Let's say masses about around 100 GeV up to 1 TeV. So we are going to be WIMPs in this moment. So the theoretical frameworks, you have different ways to study this from the mathematical point of view, but everything in the context of quantum field theory. So here is a picture in the left, the theory space, where you can find different methods, different approaches to study this, a new something beyond the standard model. So in red, you have dark matter effective field theories, which are less complete theories with a few new parameters. And then you have in green the simple extensions to the standard model. In particular, we are going to focus on this little green circle here, Higgs portals. And in blue, you have the UV completions, which are basically more complete models. The most well-known probably is supersymmetry, for instance, but you have other options. And here, for instance, as I said, we are going to focus on the green approaches. So let me introduce you via this simple model, the gauge singlet extension. So when you add this scalar field, the S field, you can introduce, well, odd, assuming that is odd under a new Z2 symmetry, you have this mass parameter and the Higgs portal. So after electroweak symmetry breaking, you get a new contribution to the mass of this scalar coming from the Higgs field, but at the end you get two parameters, relevant parameters, to describe the phenomenology of this model, at least from the point of view that I'm going to talk to you in this moment, which is the thermal paradigm. So the thermal paradigm states that basically in the early universe, if you want, in the radiation epoch, the this scalar that we are introducing was in thermal equilibrium with the rest of the particles of the standard model. That is to say, basically what we observe in figure 3, that the reactions were going in the forward and backward direction all the time at similar rates. But as the temperature was decreasing, there was not enough energy to produce, it was not longer enough energy to produce these scalar particles because they were too heavy at that moment. So basically the reactions start to go from left to right. So when figure 4 is exemplifying this fact, you have also to take into account that it start to occur annihilations of these scalar particles, but at the same time there was occurring the Hubble expansion. So at some point you expect that the particles were drift apart in such a way that they cannot, they couldn't annihilate to each other anymore. So you basically get what is called the freeze out, and finally the relic abundance. So in a more specific way, this is the typical way to describe this phenomena via the Boltzmann equation. This is the simplest way to present this equation, which basically gives you the information of how fast is changing the abundance of your dark matter particle in this case. So Y from now on is going to be the number density of particles, and X is the inverse of the temperature, which basically for this for the application that we are going to see goes from 1, basically X goes from 1 to infinite. So the main point here that I want to stress is that the rate change of Y here goes proportional to the interaction of your dark matter particle with the standard model particles. So when you solve this system, basically you can use different ways different tools if you want to solve this differential equation, even Mathematica, even with Mathematica, but at the end you have this solution, basically the typical solution for this Y variable, which is in figure 5. So basically the particle at high temperatures was in thermal equilibrium, which is the black curve, but at some point the annihilations start to the reactions started to go from left to right, as I show you here. Start to be, you have more annihilations from the dark matter particles, and so its abundance starts to decreasing. But at some point, the Hubble rate produces this freeze out. So, which is shown in this with these color lines. So basically here you can see that the bigger is the annihilation cross section, the lower is your final relic abundance, or your final your final yield, which is basically what is shown here in 4. Basically, what we observe in the left, the parameter density is proportional to the final yield that you obtain after solving this Boltzmann equation. So, but not only that, that occurred in the in that paradigm, the thermal paradigm was occurring in the early universe. But today we have some ways to explore these to test these models. So one of the most famous is direct detection, which is this one. It's shown in this plot, with the most recent, most powerful tool in its class, which is called Xenon 1T. And basically it's a liquid xenon in which you expect some recoil of your nucleons due to the scattering of your dark matter particles that are surrounding us in this moment. So diagrammatically is basically what we have in figure 7 via Higgs portal. This in the above right, you have the cross section for this model, which you can find in some papers. And at the end, so considering the cross section, you can, and the sensitivity of your experiment, you can constrain your parameter space, the parameter space of your model. As you see here, we have a Higgs portal in the left, and the x-axis, we have the mass of the dark matter particle. So if you see, there is a black line here, which gives you, correspond to those points with the correct relic abundance, 0.12, basically for the parameter density. So points below, that means Higgs portal couplings smaller than those values for a fixed mass give you they give you an overabundance because the strength of the couplings are too small. But above that curve, you can have, for instance, an underabundance of your dark matter particle, and that is not excluded in principle, because you can say that this model is not the last word to explain dark matter. So maybe this model is giving you a little fraction of the total budget. So as you can see, if xenon 1t is this curve, which basically eliminates most of the parameter space, but the Higgs resonance here, it's not possible to eliminate it completely. But as you can see, most of the masses above even the TV scale are ruled out by this experiment, even if you are not considering this this dark matter candidate as the only source. So the question is there a way to reopen the parameter space at the electroweak scale, considering an extension to this model, for instance? And that is what we studied with a
I'm sorry, I have a question related to the previous plot.
Sure.
So typically in direct detection experiments, you experiment a loss of sensitivity when you go to lighter masses. And I don't see this feature in this plot. Is there any particular reason for this? Or it happens, just that you're not showing it?
Yeah. Actually, here you don't see lower masses because it is cut. The mass range is cut off at around 50 GeV. But yeah, if you go at lower masses, for instance, you have other constraints here, which is not only the direct detection experiment, but coming from the Higgs, the width of the Higgs, the decay width of the Higgs to invisible from LHC. So, but sorry, your question was whether there is enough sensitivity at lower masses?
So typically at low masses in direct detection experiments, you will see that you lose sensitivity simply because the dark matter doesn't have enough energy to produce a kick in the detector above the threshold. But yes, I don't see that in this plot, but maybe it's only because, you know, I'm not seeing the whole mass range here. I don't know.
Yeah, it is, as I said, it is cut off here at, it start around 50 GeVs, so you are not seeing below. But okay, at the end, yeah, but at the end, is the sensitivity of this synonym 1T experiment start, I think, around 5 GeVs or 10 GeVs. So even at those masses, the predictions of the model are ruled out by this experiment and also by LHC bounds. So you don't have masses at those. You don't have a parameter space at those masses.
Okay, thanks.
Mm-hmm. So basically, considering what we consider here is a simple extension with two real scalars. So as I said, two real scalars, but we are going to focus on a particular scenario, which is called assisted freeze out. Then I'm going to show you some results and the conclusions of this work. So the extension is very simple. You have the two scalars, which now each of one transform under its own discrete symmetry, whereas the standard model content transform in a trivial way under these two symmetries. So you end up with this potential. Now you can see that you have the typical terms of a singlet, a gauge singlet, and the two Higgs portals, for instance, in the right, but also you get this interaction term between the two scalars. So this is this is an important term that we are going to take into account with this dimensionless parameter, lambda1, 2. So after electroweak symmetry breaking, basically we get the same, the two masses for the two scalars. The relevant parameters are this one, the two masses, the two Higgs portals, and the interaction between the two scalars. Here, just a set of the three-level diagrams of the dark matter particles, or the stable particles in this case. So yes, as basically I just want to show you the equations, not to scare you, but I think that it's necessary to at least to get a feeling of the Boltzmann equation of this system, which looks complicated, but they are not so much. But basically here we have now we have two dark matter particles or two stable particles. We need to look for their abundances of each one. And it results that here you see that the two Boltzmann equations are coupled to each other. And so, but basically we have the same than before, which is the first term in each equation is the Higgs portals, each dark matter particle annihilating into the standard model particles. And the rest of the terms basically are the interactions of the possible annihilations of one dark matter particle into the other. And here there are some Heaviside functions which take into account the hierarchy mass of the scalar. So if for instance, the mass M1, the mass of the first scalar is bigger than the second one, you keep just the first term because you have only annihilations of your the first scalar into the second one. There's no enough energy to the opposite in that sense. And okay, and Y with this subindex E are the equilibrium densities, and lambdas contains basically some constants in it, but the important thing is, or the main important thing here is that it's proportional to the average annihilation cross section times velocity. So this is the system that we have now. And again, so we solved this system using our own code and actually with cross-checking with micromegas. And now we have that the total relic abundance is the sum of each one dark matter particles, and the same. So yeah, the same parameter density for each particle. And this model has been studied before by these people that appear here. You can look at it if you want. And they studied this with the two Higgs portals with sizable values. That means with values above 10 to the minus 3. And they found that it is possible to have these dark matter particles with masses above 800 GeVs. So in that sense, they could reduce they could see that it's possible to have dark matter masses with even with masses below the GeV scale, but not too much. But you gain some parameter space in comparison with the SHP, the single Higgs portal. So the question now for us was basically, what about if we set this scenario in a specific one in which we turn off the second Higgs portal of the S2 particle. So basically it means to take this lambda h2 equals 0. And that means that only S1 will interact directly with the Higgs, but as the two dark matter particles interact between them, S2 will be thermalized by the assistant of S1, which is already in thermal equilibrium in the very early universe with the rest of the particles. So when you do that, basically that term in yellow disappears. The equation reduced, simplified in that sense a little bit. And these are the results that we have found. Basically, in the plots, in the left, for instance, we have the relic abundance, the parameter density of each scalar as a function of the mass of the second scalar. And in green, we have the total relic abundance, the sum of it of the two. And if you see when the mass M2 is lower than M1, we obtain a huge hierarchy between the relic abundances of each scalar. Whereas when the M2 mass is bigger, we have this behavior which, in principle, when the degeneracy is not too big, we have that the abundance of the S1 particle is the leading one, but when the shift mass grows, you get basically that S1 abundance become the subleading. But we have checked that it's the most interesting part was basically when we have this hierarchy, M1 bigger than M2, because here in this regime we can obtain two low relic abundances for omega 1, or sorry, for S1, the first dark matter particle, which is the particle that can be seen at the experiments. Here in the right, so yeah, this means that if omega 1, the blue abundance is much smaller than omega 2, we will get some suppression in the cross section of your S1 dark matter particle, because now the expression of your cross section will be weighted by this factor, because it depends on the density of your dark matter particles in the laboratory or around the Earth, if you want. So we expect a suppression in this sense, and as it is shown in the right plot, basically we have plot the same, but in terms of the interaction lambda 1, 2 of the interaction between the two scalars. And if you see in the dashed lines are the same hierarchy that we are interested in here in this part of the plot. So if we increase the interaction of the two dark matter particles, you can see that the abundance of S1 decreases. And that is what we want. Whereas the other scalar, it remains practically constant at higher λ1,2 couplings. So this is the idea, the main idea, to look in those regions. And after scanning the parameter space, we have found these results that are shown in figure 11. Basically, this is a scan, a random scan in the projected in the parameter in the coupling in this plane of the couplings, λ1,2, λH1, fixing the mass. In the first plot, we have fixed the mass M1 to 100, and the points shows with the color the mass of the second scalar, which we see. We just saw that M2 must to be lower than M1 in order to have a low relic abundance for S1. So you can see first from this plot is that, yeah, the first lesson is that λ1,2 take very high values, and the parameter space is it's much more reduced in that sense. Considering that if your criteria of perturbativity is 4 pi, for instance, you get just those points at very high values for λ1,2. And if you go to higher masses, you get a more reduced parameter space, as is shown in the right plot, with higher couplings for λH1, for instance. So the delta, which is the mass difference between the two scalars, is not bigger than some dozens of GeVs, as it's shown in these plots. So basically, as we saw these high couplings, we studied what about the Landau poles? Because even if you are in the perturbativity regime, you have to be aware of how fast grows your couplings with the energy, especially considering that this is a model that can be context in a cosmological scenario. So in that sense, the most important RGE equation is for this high coupling, λ1,2, which goes proportional to the coupling to the square. And of course, as we have seen that the values are too high, they will grow so fast. And in the right plot, we see that basically the maximum scale of the model allowed as a function of λ1,2 until the model, before the model get or passes the perturbative limit, or in other words, gives you a Landau pole. So for instance, considering, as we have seen that in the first plot, for instance, we have couplings λ1,2 with values 6, for instance. You can see that if we start from there, you cannot go with this model much above 7,000 giga-electron volts, for instance. And if you go to higher λ1,2 couplings, your effective description gets very limited. So in that sense, this is a disadvantage of the model because it has a very limited range of applicability, especially, as I said, if you want to study this model in a more at higher energies. So in that sense, you need to go beyond. So, but I'm going to say about something about that in the last part of this presentation. So basically, this work was based on the constraint that we have seen not only with the scalar gauge singlet dark matter at the electroweak scale, but you can see that in the literature there are a lot of models which has been very constrained, especially by Xenon 1T experiment. So there are different options to evade that fact. And in particular, we went to this extension with two real scalars in a particular framework in which we turned off one of the Higgs portals, but we have seen that the couplings that you get are too much high, because the Higgs portals basically are they are under testing, if you want, under the direct detection experiments directly. So actually, this model has been studied before in this paper, Mighty et al. But they didn't explore in too much detail the parameter space, and also they didn't have study the RGE evolution of the couplings. So in that sense, our work went a little bit beyond that, and we could see the limitations of the model in that sense. So yeah, that is the first part of the work, which was the biggest, I would say. And the second part, if you have any question or some comment. Not at this moment. Okay, so basically this is I'm going to finish with this. It's not too long. Basically, and this is the second work that was, as I said, carried out with Karim Gorgobani from Iran, and it's an extension of the previous work. Basically, now introducing a new fermion, a vector like lepton, in order to account for this G-2 anomaly. So this is the outline. This is a picture just of the Fermilab at Fermilab with this the detectors, the experiment, basically transporting the experiment here. So just a little introduction. The magnetic moment of the muon, as you know, is given by this expression. The Dirac equation predicted that this G factor is equal to, but some experiments in this year, 1947, around those years, people start to realize that maybe these parameters G were not exactly what was predicted by the Dirac equation. And one of the first persons that studied this, the value of G at the quantum level was Schwinger, the picture in below here. And he found basically that this value under quantum, actually at one loop level in quantum electrodynamics, was basically this value. A tiny correction, but it can be observable. So nowadays we have two very precise values, one from the experiment and the other from the theory side. And as you can see, they are very close to each other, are basically the same numbers than that I was showing you here, predicted by Schwinger in this elegant expression. But yeah, with much more precision now. But still there exists a discrepancy between the two quantities at the level of 4.2 sigma. And as you can see here in the picture, we have this discrepancy between the standard model and what is observed at the experiment. So the question is, what about if this anomaly comes from new physics related to dark matter? And there are a lot of papers and people that has been studying this deviation from this point of view. But I think that we ended up with a model which is, in my opinion, is one of the simplest. Because you don't have to deal, for instance, with bigger representations than for SU2. That is just an example. There are, so yeah, let me basically resume you what we have done here is the same than before, but now the psi field, the vector like lepton, now transform in an odd way only under the first symmetry. In that sense, you end up with this Lagrangian. The second line is the same one than before, but in the first line now you have an interaction term allowed by the symmetries between the right-handed muon S1 scalar and the C and the vector like lepton. So what we expect is at one loop level, this is the diagram, which is basically giving you the contribution at the theory level in order to be more close to the experiment value. And this, as you can see now, we have the fermion, the vector like lepton running in the loop, and S1, only the first scalar also in the loop. The expression is very simple for the deviation at the one loop level, and it depends now on three parameters, new parameters, which is the coupling, the Yukawa-like coupling, kappa 1, the mass of the fermion, and the mass of the scalar S1. So basically, we did the same done before. We said that the mass hierarchy must be this one. The first inequality is the same than before in order to have most of the dark matter coming from the second scalar. But we said that the mass of the fermion must be above M1. Otherwise, you will have an unstable S1. It would decay into the vector-like fermion, vector-like lepton, and a muon particle. So this is the set of Boltzmann equations. Now, the only difference now is that we have in this lambda 1,1xx a new interaction, which is the interaction, a TU channel, in which the S1 particle annihilates into two pairs of muons, a pair of muons, yeah. So plus Higgs portal corrections. But they are not, I'm going to show you that they are not relevant for the phenomenology, at least, of this scenario. So basically, people have, let me just show you the plots that were the main motivation for this extension. And in the left, in figure 14, you see these plots, which are the results when people study the simplest model to account for dark matter and the G-2 anomaly. In this paper, Atron et al. With this number. So this, what they obtained was based on a model with only with the first scalar and the vector like lepton. So in that sense, when you have only that, you can see here in the plane of the masses, here M phi correspond to the mass of S1 in this in our language. So basically, you can see that the red curves here give you the correct relic abundance for considering yeah, lambda r is our kappa. Sorry for there are some differences in the nomenclature. Lambda r is our kappa, sorry, is basically the Yukawa-like coupling here. And phi here is S1. So the gray region, for instance, and the gray and orange regions are excluded by LHC. The cyan color above is excluded because it would make the scalar unstable, and the green regions here correspond to those points in which you can obtain the delta A for the G-2 anomaly, the correct value. So as you can see, the relic abundances of that model gives you, it's already ruled out. It gives you something that is already excluded. And below that curve, you have an overabundance, and below that curve, you get an underabundance. So the question was basically, what about if we move this curve, red curve, to the allowed region, and with that curves passing through the green region? So yeah, basically in other words, here in the left, sorry, in the right plot, we show the yield of the dark matter as a function of the inverse of the temperature, and in the green continuous line is basically the prediction of this model, of the left model, the minimal model, and for considering a point, a parameter space point, which gives you the correct value for G-2. But as you can see here above, it gives you an underabundant value for the relic density. So if you consider, for instance, the continuous lines in this plot, you can see that the blue one corresponds to the abundance of S1 in our model, whereas the red continuous line is the abundance of the S2. So the blue line and the green lines, continuous lines, are very close to each other. So with the red, with the other component, we are completing the rest of the missing part of the dark matter. So that was the idea. And as you can see here, for instance, the omega 2 h square gives you the correct relic abundance. And yeah, just to finish here, not considering the Higgs portal, here we have shown these the results in the plane of the same parameters than before of the previous figure 14. So the mass of the scalar 1, which interacts with the vector-like fermion, and the mass of the vector-like fermion in the x-axis. And as you can see, again, our curves or our predictions now cross the green region for different. We have shown the predictions for different mass shifts and different lambdas values for lambda 1, 2, the coupling between the two scalars. And in the right, we just plot the same, but with a bigger Yukawa-like coupling, 3.5, which is very close to the perturbative limit according to some works in this type of models. So yes, basically the degeneracy of the mass shift between the scalars is not much above 5 GeVs in order to account for this for the correct relic abundance, for the G-2 excess, and evading all the constraints. the rest of the constraints, LHC, etc. So yeah, let me finish here. Here, this is just the when you turn on the Higgs portal, what happens. But at the end, if you are interested, you can see the paper in which we explain a little bit more about this. But it's basically the Higgs portal when it is open, and at the same time you consider the direct detection bounds on it, you will find that there are no deviations on the results that we have found in the first place. So, so in this, the conclusions, basically in this second work, we have studied this extension with the two scalars, the two singlet scalars and the one vector like lepton. And we have seen that we can obtain the correct relic abundance with G-2, evading the different constraints, collider constraints in particular. Now, we have seen very fast that the Higgs portal couplings don't interfere in the results that we have obtained in this model. And last but not least is that this model also presents lower couplings for this lambda 1,2 parameter in comparison with the first work in which as I told you, this lambda 1,2 got very high values. In this case, we could evade those big numbers in such a way that the model can behave better at higher energies. So yeah, that was all. Sorry for it was too much maybe.
Don't worry, it's fine, it's fine. Thank you very much for the nice talk. Does anyone have any question? I think
maybe
not.
it was too clear.
Maybe. No, but I have a question because I got lost a little bit at the end. Can you tell me you had the plots with exclusion zones where you have the red curve for the, before.
That?
Before, okay. That one. Can you tell me a little bit, I got lost in between the difference between, I know that this one is previous work, so the next plot is what it was, what you did, right? So what is the difference in the models so that this curve was allowed to be in the not excluded region?
Yeah, so the question is, what is this? What's the difference between the model here in figure 14 and with the model in figure 16?
Exactly. So yeah, what you changed so you could be in the allowed region?
The only difference is that we added a new field in our case, which is S2, the second scalar, second singlet scalar.
Okay.
This model, the minimal scenario is what I call here S1, one scalar, singlet scalar, and one vector-like fermion. And you obtain this. But if you introduce another scalar, you allowed, which is invisible to the experiment, S2, because interacts only with, you force that it will interact only with your first scalar via this. We are turning off the Higgs portals. Forget about the Higgs portal, but your second scalar only interacts with your first scalar, and under the symmetries that we have imposed from the beginning, it doesn't interact neither with the vector-like fermion. So only you will have basically this interaction, and in that sense, it participates in the relic abundance calculation, and it gives you what was missing here in this. But basically, the second scalar now carries most of the dark matter relic abundance.
Okay. Okay, thank you. Now it's clear. Thanks. Is there any other question? I think not.
If someone has a question or whatever, can write me also.
Yes,
I
I have Bastián's email if you have any questions. Good. Okay, then that's it for today. Again, thank you very much, Bastián, for your seminar today, and we will see each other again next Thursday for the next seminar. Thank you very much.
Okay, thank you, guys.
Bye-bye.
Bye.